Hi everyone. So the reason I'm so fired up about week 7 is that this is the time when we actually start to build our own proprietary model. It's when we start to build our own AI, and we are looking to build something that we're going to try and make to compete with frontier models, or yes, even we're going to try and see if we can outperform at least some frontier models. Now, the reason that that's even possible is that we are trying to solve one particular specific problem where we have a lot of data. And so we can take potentially a model that is significantly smaller than a frontier model. We can take something like an 8 billion parameter model, and by making it very good at one focused task, we can compete against the giants like GPT-4o. Because even though GPT-4o has trillions of parameters, it's designed to do so many different things, including writing witty poems about presidential candidates. We are not going to be able to do any of those things, but we are going to try and get really, really good at predicting prices of products. That's going to be our thing. That's our business problem. That's what we're setting out to solve. The first step in this is to decide which model we're going to use as our base model for fine-tuning. And that's something that's worth taking time on because it's going to be obviously pivotal to what we end up building. You can think of it in itself as like one massive great hyperparameter. We can try a different base model and see how that performs. As part of that, we're going to have to decide whether we take the original pre-trained version of that model, the very base model. Sometimes people use the word foundation model to describe that, as opposed to the one that's been fine-tuned for chat purposes, that's sometimes called the instruct variant, which is the one that's expecting a list of dictionaries with user prompt, system prompt, user assistant, and so on. That style of input, which you'll remember gets turned into just a series of tokens separating out different sections of the prompt. So we've got to make a decision about that, and there are, of course, pros and cons. And then once we've done that, we should then take the base model as it is off the shelf and see how that does against our challenge, because we see whether we're already in a position where we are competing with frontier models. And even if we're not competing with frontier models, remember that this is going to be free of charge, or at least it'll be the cost of us running compute. So we won't have to pay API costs when we're running our own open source version of the model. So even if we're in the right territory, there's still many reasons why we should use open source even before we talk about making it into a proprietary model specialized for this particular business problem. So anyways, with that in mind, it's time for us to talk about which model to use. First of all, we need to decide how many parameters to use. And, it is probably a case that more is more. More parameters is going to give us a better shot at solving the problem well, particularly in a world as we have it, where we have a lot of training data. We have 400,000 examples. So we've got tons of training data. It's not like we're limited in that regard, and we could always generate more if we wanted to. So really our constraint is going to be, the amount of memory capacity that we have. We're going to want to fit it in one smaller box. And so we pretty much already know at this point that we can get in about 8 billion parameter model, 7 to 8 billion parameter. We won't be able to go much more than that. And whilst there are some small parameter models, very small, like Gemma goes down to, I think, a 2 or 3 billion parameter version. We'll take a look in a second. We're probably going to want to take 8 as the largest possible model that will fit into the boxes that we can afford. So that's going to be our approach. When it comes to the base or the instruct variants, there are pros and cons, and it's something to experiment with. Generally speaking, if you're fine-tuning specifically for one problem where you have a particular prompt that you'll be using and expecting a response in a particular way, then you might as well start with a base model, not an instruct variant, because you don't need to apply things like system prompts and user prompts, because you're just going to be training it for one purpose anyway. So you might as well just take a base one and fine tune it so that all it's really good at is that one task. So that's the kind of default answer. Now, there are some benefits to starting with the instruct variant. One of them is that it's very good. It's already been trained to recognize things like a system prompt and the user assistant interaction. And you can use that to your advantage by using the system prompt to sort of tee it up in a certain way, to frame it, to be working, to be taking a persona, rather than having to rely on it learning that persona through all of your training data. So there are some situations where the instruct variant is a better starting point. Now, for us, my instinct is that base is the better starting point because we've got such a set structure that we're going to be using for all of our training data and for our objective. And I've in fact tried both. And base did do slightly better than the instruct variant, but they were very close. You could also try both and see if you get the same results as me. But I would think it would be more normal in our kind of situation when you have one particular task and you don't need to be applying system prompts and the like, that you would start with the base variant. But with that introduction, let's head over to the Hugging Face open leaderboard and take a look at some models. And we've returned to the Hugging Face open LLM leaderboard, the first place you go when selecting your base model for your training. So first thing I'm going to do is I'm going to focus in on models with a parameter size at most, let's say 9, and we can afford to go down a bit. And let's filter out everything but the base models to start with. And let's have it show the number of parameters as well. Here we go in this table down below. So this is the results of the strongest models according to these various metrics. And you will see that powerhouse Qwen that I've mentioned many times, including this 2.5, Qwen 2.5 is very new, 7 billion variant is the highest scorer of this lot. And you'll see that Gemma, there's a 9 billion parameter variant of Gemma that's right up there too. Mistral up here, and the one that we like to talk about a lot, there was Phi 2, by the way, from Microsoft. LLaMA 3.1 is a little bit further down. Now, it's worth mentioning that the numbers are all reasonably close at the top, although there's somewhat something of a margin here. So it might concern you that LLaMA 3.1, that you happen to know is one we're going to end up picking because you've seen it in the code, is further down. But there is something of a reason for that. When you're looking at these different scores, really you do need to also bring in the versions that have been trained, what's called the instruct variants, which are the same models but then given more trained using various reinforcement learning techniques to respond to that particular chat instruct style. And when it's given that kind of framework, it's more likely to be able to perform against these various tests because it will respond to the instruction it's being given rather than being expected to be trained to adapt to a different task. So really you're getting a more realistic view of the capability, even of the base model, if you look at how it performs with benchmarks when you look at the instruct variation, if that makes sense. And when we do that, we see that LLaMA 3.1, 8 billion really is in the top grouping here. We've got Phi 3 is up there as well, Gemma, and then the Meta LLaMA 3.1. So it's doing very well when you look at the instruct variant. And as I said, somewhat perversely, I'm not suggesting that we actually use the instruct variant. I'm suggesting that we stick with the base version of it because we don't want it necessarily to have used up lots of its thought process, lots of its sort of training power, learning about things like system prompts and user prompts and so on. I'm just saying that once you have been through that exercise, you can see it performs well in all of these scores. And that gives us a good sense that the base model is good at adapting to be able to address these different benchmarks. So that's a more nuanced way to interpret the results of the leaderboard. You can look at the instruct variant and see how that performs, and it still gives you a good indication of how the base model will perform as well. Now, there is one other slightly subtle reason that I'm picking LLaMA, even though you might say that either Phi3 Gemma or indeed Qwen would look like they are scoring higher in many fronts. There is a convenience to LLaMA that's just, it only makes a small difference to everything, but it does make our code a bit simpler, and it makes the task a bit easier for LLaMA, which is that when you look at the tokenizer for LLaMA, you'll see that for LLaMA, every number between 0 and 999, every 3-digit number gets mapped to one token. The same is actually not true for Phi3 or for Gemma or for Qwen. In all three of those other models, they have basically a kind of, you could think of it as like a token per digit. So the number 999 ends up as 3 separate tokens. Now, you might ask me, what difference does that make? That it shouldn't make any difference at all. So it's going to turn out that when we're doing training, we're using a model to generate tokens, and we're trying to make it think in terms of more of a regression model. We want it to be trying to solve for getting better and better at predicting the next token, and that should map to the price. So it simplifies the problem. If the price is reflected exactly in one token that the model has to generate. So just in this particular situation, for the particular problem we're trying to solve, the tokenization strategy for LLaMA 3.1 works very well, because the single next token that it generates will in itself reflect everything about the price, so that it's not the case that it might predict that the next token should be 9, and that could be $9 or $99 or $999, and that will only transpire when it does the token after that. No, it's going to be the case that the single token that it projects as the next token in its answer will reflect the full price of the product in one token. So it's a nuance, but it's a reason why we lean towards selecting LLaMA 3.1 in this case. But by all means, we will have the ability to choose other models and see how they perform. But LLaMA gets a bit of an edge because of this convenience with the way that it tokenizes. So that gives you some color on some of the thought process that goes behind selecting a model, looking at the leaderboards, looking a little bit more deeply at leaderboards, thinking about instruct variants versus the base models, parameter sizes, and then also some nuances about things like the way that the tokenization works. And all of that together has allowed us to come to the decision that we are going to select LLaMA 3.1 8 billion as the base model for our project. And now with that, let's go to the Colab and give that base model a try. Welcome to Colab. Welcome to the week 7 day 2 Colab. And just before we try our base model, we're going to actually see these tokenizers in action. Start with some pip installs and some imports as usual. And now in the constant section, I'm going to set up 4 different tokenizers that we will just quickly look at. After that, we're going to look at our base model, LLaMA, and do some work with the data. And I've also got the constants here for writing to the output in color that you may remember from when we visualized results in the past. All right, let's run that. We log into Hugging Face using the usual snippet that you know well at this point. And now I've written a useful function called investigate tokenizer that takes a model name. And what that does is it will load in the tokenizer for that model name. And it will then iterate through these 6 numbers, 0, 1, 10, 100, 999, and 1000. For each of those numbers, it will convert it into a string and then ask the tokenizer to convert that string into tokens. So what are the tokens that represent the string 100 as a piece of text? And I'm using this add special tokens is false parameter. What that means is, please don't add in things like a start of sentence token and an end of sentence token or something like that that will interfere with things. Just simply convert this text into tokens that represents that text. So that's what it will do, and then it will print that out. So to run that and to show it, let me call investigate tokenizer, and we will start by calling it for the LLaMA 3.1 model, and let's see what we get. So what we get is the string 0, text 0, converts to the token number 15. 1 goes to the token 16. 10 goes to token number 605 as it happens. And you'll see that similarly 109.99, they each map to a single token. 1000 though, that maps now to 2 tokens. In fact, it maps to the token for the number 100. If you see that, followed by the token for the number 0. And that, so just as you would imagine, it is the tokens for the text 100 followed by the text for a 0. And what you see here loud and clear is that if we're just focusing on 3-digit text numbers, on 3-digit numbers, we have this useful property that whatever price we have is always going to map to 1 token. So the model's task of trying to predict the price of a product will end up being just predict 1 token and get that token right, and then you've got the right price of the product. And so it's not an essential property. We don't require that. These models are perfectly able to generate a sequence of tokens, but it's convenient that we're going to simplify the problem down to just getting this 1 token right. And we can also see how this looks for another model like Qwen 2.5. And now we see something different. The single digits 0 and 1 mapped to a single token, but 10 mapped to 2 tokens. In fact, the token for 1 followed by 0. 100 is 100. 999 is presumably 999. And 1000 is 1000. 4 tokens being used there. So you see that different property, and hopefully that really clarifies why I think LLaMA 3.1 has an edge. Gemma 2, Gemma 2, similar properties to Qwen. Interestingly, totally different vocabulary. It's a much bigger number, but that's no surprise. There's no reason why they should have the same vocabulary. Yeah, it's clearly not a 1 token for 1 3-digit number. And Phi3 is, as I say, similar. There is actually a different variant of Phi3, a smaller variant that has the same nice property as LLaMA 3.1. So that is another thing that would be worth potentially trying. As could any of these be tried. It's not a disqualifier that it produces multiple tokens by any means. All right, well, anyway, that gives you a background to the tokenizers and a good sense for why we picked the model that we did. In the next video, we will then load in data and try testing our model. So you may remember eons ago when we were building our data set, at the end of that, we uploaded our data to Hugging Face. Since that point, since we also produced pickle files, we've been loading in the data from pickle files from that point onwards. But now that we're in Google Colab, it's easiest for us to collect that data back from the Hugging Face hub again, which is a very typical task in this kind of process of building your own model. So here I go. I load the data set using Hugging Face load dataset method, passing in the dataset name, and then I break it up into a train and a test. And the dataset name I set in the constants at the top. Once I've done that, we can take a look at the first training data point. And what it looks like is it has text and a price. You may remember we set this explicitly ourselves. The text is our prompt. How much does this cost to the nearest dollar? Followed by the description of the product, followed by price is dollars, and then the price itself, but rounded to the nearest whole number. And in the top here, I say, how much does this cost to the nearest dollar? And the reason I'm doing that is I want to make the task a bit easier for the LLaMA 3.1 model with its puny 8 billion parameters. when we were sending it to a frontier model, we didn't need to specify that because it's easily powerful enough to make its own decisions about sense. But in this case, we want to give our model every simplicity we can. And since this will always map to one token in LLaMA 3.1, we're making it quite easy that all it's got to do is be able to predict that one token right there. That's going to be what it's going to try and learn how to do well. And in this data set, we also have the real price in here too. If I look at the test data and take the first point, the test data going to look very similar in structure with one tiny difference. Do you know what that difference is? I'm sure you do. It is, of course, that there is no price provided at this point in the test data. The text is going to be the text. How much is this to the nearest dollar? And then we pass in this text. And the assignment to our model is to predict the next token. What is the probability of the next token coming after this? And we hope it will give a high probability to the token that matches the number that is 374, matching the actual price. And so that is the assignment. And because this maps to one token, it's really, the challenge is just to get good at predicting the next token, the single next token that represents that cost. One other point to mention is that you may remember we did some futzing around to make sure that this text always fitted into exactly 179 tokens or less. And because of that, we're able now to tell I've got a constant up here that says maximum sequence length is 182. I've added in a few tokens there. It is, in fact, 179, but I'm adding in a few extra spare tokens because the tokenizer is going to add in a beginning of sentence token to the start of the sequence, and it may add in an end of sentence or a pad token or two at the end. And I want to have no risk at all that we accidentally chop off the price, the most important token, which is going to come at the end of this. So given it a little bit of extra leeway. In fact, this doesn't become important until we get to training, but I wanted to point it out now since we're looking at the data. So there we go. We've just gone too far. We've just looked at this data. The next thing that we do is we pick the right quantization config. I set a constant up above, quant4bit. In this case, I set it to true. Let's just go and check that. We will see, there we go, quant4bit is set to true. And so now when I come back down again, we're going to pick the 4-bit quantization. And I show you here what it would look like if we picked 8-bit, but we're going to pick the really minuscule 4-bit version. And then we load in the tokenizer and the model. I'm not going to run this cell because I already ran it. You can see it's sitting in the memory here. If I run it a second time, I'll run out of memory. What we do here is we load in the tokenizer. There's a bit of stuff here that's very boilerplate that you'll see a lot. We're telling the tokenizer that if it ever needs to pad the end of a sequence, it should just use the end of sentence token and just have that repeatedly. And it should do that off to the right-hand side. This is standard stuff that will happen when we train. We won't actually use it right now. So you don't need to worry about it, but you'll see this all over the place. It's a very standard setup, as is this line here, which you also don't need to worry about right now. What we're doing is creating a tokenizer and loading in the LLaMA 3.1 base model. And it's using up the 5.6 gigabytes of memory that you're expecting. There it is, 5.9 it seems, because I've done some inference down below. Yeah, it's the very slimmed down 4-bit version of the model. So now this function is one that should be familiar to you because we used it recently with frontier models. Extract price, which is going to take some text, any text, and pluck out from it the price that's being predicted. And so if I do something like extract price is $999. This is a string perhaps, so that's not going to work very well, is it? Price is $999, blah, blah. Price is $999, so cheap. Whatever. Then hopefully what we'll see, yes, is that it's going to pluck out 999. But the model, we know it's going to be provided with this in the prompt. It's what comes next has got to have 999 in it. And then this here, model predict. So this is the function which we're going to be using in our test harness. This is the function where we tell it, we're going to give you a prompt and we want to know how much does this cost. And so this is how we call our model in inference mode, similar to what we did several weeks ago. We take the prompt and we encode it using tokenizer.encode. And this thing here will push it off to the GPU. This is just something that's not super important. It stops it from printing a warning. So this doesn't actually affect anything. And then, to be precise, this prevents it from trying to predict anything that's happening in that input token area, which we don't want it to predict that. We want it to predict what's coming afterwards. That's what it would do anyway, but it would give a warning if we didn't explicitly tell it this. So then we say for our outputs, we're going to call our base model, LLaMA 3.1, and we're going to call the generate method on it. We pass in the inputs. We're going to say the maximum new tokens we own is 4. We could make that a much smaller number. We only really need 1 token. I'm giving it to generate up to 4 tokens just in case it prints another $sign or something like that. We pass in the attention mask that I've just set that stops it giving a warning. And this is just saying we only want back 1 answer. We don't want it to come back with multiple answers. And then for the reply, we take that 1 answer, it sends us back, and we call tokenizer.decode to turn that back into a string, and then we extract that string. All right, so that's exciting. Let's just remind ourselves. So if we take the first test item, here it is. It's the OEM AC compressor. The actual price is $374. Who knew? So let's have our first shot at this. So we're going to say model predict test 0, and to get the prompt out of that, I just call text on that. So are you ready? Here we go. LLaMA 3.1 base model is going to try and predict the price of an OEM AC compressor with something repair kit. Okay, and it's predicted $1,800, which is rather far off. So that is potentially a bad omen for how the LLaMA 3.1 base model will work, but we might have just gotten unlucky with the first example. But that will be revealed in the next video. Okay, it's moment of truth time. I have just taken our class tester. You remember this class? It's the class that runs the evaluation across the full 250 data points from our test data set. It's slightly different. If you go through this, you'll notice there's some very subtle differences because we're not taking an item object. We're taking a data set, a data point from our data set. So there's a couple of small differences, but otherwise this tester is basically exactly the same in terms of what it does. And it ends, of course, with this single line, tester.test. The model predict is the function that we just wrote that tries out our model against 250 points, and we pass in the test data set. And of course, I've already run it. And let me scroll through the results so you get a sense. It's right up at the, there we go. We'll take it to the top. So you'll see there, of course, that first red item is where it predicted $1,800 for something that cost $374. There's some more reds, there's some greens. And it certainly gives you a sense that it's not like we're getting, the model understands the task. For this one, for example, it guessed $89.99 and the truth was $101.79. It's interesting that it's not sticking to the nearest whole dollar. It's still creating things with 99 cents. And you'll see that there's some other problematic ones here, but there's greens and reds, but quite a few reds. So I will put us out of our misery and go straight to the chart. Here it comes. Oh my goodness. It is a horrible, horrible result of 395 in terms of the error. 395, which you will remember, is considerably worse than taking a random guess, I think. It's certainly worse than just taking the average number of the training data set. Not that it knew the training data set. Yeah, it's generally a horrible result. Perhaps not massively surprising. It's a tiny model. It's been hugely quantized as well. And you can see visually what it's doing. You can see that it has had a few different levels that it's been most comfortable guessing at. And it's guessed most often at one of these three levels. And unfortunately, one of them is far too high. We've never told the model not to go above $1,000. It's not like that's a requirement. It can guess whatever it wants, as could GPT-4o. We've not given it that intelligence to know that, and so it's gone too high far too much of the time, and it's really ruined the results. So a poor performance from our base model. Not that surprising given the small number of parameters. And of course, the challenge on our hands now is going to be, can we take this poor performing model and use fine-tuning, use a training data set to make it stronger? And can we get close to what a trillion parameter model can achieve? So this is an 8 billion parameter model and it's been quantized. Can we get close to the trillion plus parameters in a major frontier model? Because this is open source, it's free, there's no API cost. Wouldn't it be amazing if we could perform at that level, or at least beat a human? Right now, the human beings are winning over an untrained llama. At least this human is. One final thought to leave you with. You remember that this is quantized down to 4 bits. You might be asking yourself, how would it look if we quantized just to 8 bits, if we kept the 8-bit version and ran it through? It'd be interesting to see whether how much the performance was impacting by going all the way down to the double quantized 4-bit. And indeed, you can do that, of course, and this framework gives us a lovely way to in a very simple, tangible way, see the difference. So remember, 395 is how far this is wrong. So in this other tab, I have just run it with the only quantized to 8 bits. So if I go up to the top, you can see that I've got up here quant 4-bit set to false, and otherwise it's exactly the same notebook. Let's scroll all the way down and go straight to the results. Looks like it's in here. Hold on, build the tension. And here we go. So it's also pretty horrible performance, but it is better. 395 became 301. And that's not surprising at all. You know, it's got twice the amount of information. You know, again, quantizing did have an impact on accuracy, but perhaps we would have expected the 8-bit model to have done even better. So there wasn't such a great difference between them. But it does show you, of course, that the bigger model is able to do a better job. All right, with that, that's been pretty interesting, pretty revealing. Let's go back to the slides to wrap up and summarize. And it's this time again when we look at the podium of how our models are performing across the board. You already know the answer, but we should look at it anyway and have a giggle. So we first look at the constant model that just guesses the average value from the training data set. And if we look at that number, it was 146. It's looking distinctly lower in here right now, and I think you probably know why. Then we looked at a traditional machine learning model that was able to beat the average, which we would hope it would, but not by masses. We looked at the random forest approach, which was the best of the traditional machine learning approaches, coming in at 97. We did compare it with a human being and showed that human could beat the basic simple features, but was beaten by random forest model. GPT-4o was the best of the various frontier models we looked at and absolutely crushed it with 76, way outperforming this human. And then today we've looked at the unfine-tuned base LLaMA 3.1, 8 billion parameters, quantized all the way down to 4 bits. and we saw that that was at 396, devastatingly bad. And it was only slightly better when we quantized to 8 bits instead, coming in at $301 of error. So clearly we're off to a bad start with LLaMA 3.1, but in some ways that's exciting because the challenge is on. We've got the model here ready for us to try and explore how we can make it better. And our target is to try and be competitive with a model like GPT-4o, which is, has trillions of parameters. If we can be competitive with that in this particular task, and we can do it with an open source model that's for free, then we have achieved a great thing. Okay. And so, in summary, at this point, at this juncture, you have reached 80% of your way in this journey, and that is absolutely fantastic. I'm so happy you are sticking at it. I'm so happy you're here. I gotta tell you, the 20% that's still to come, it's the best. It is the best. The juiciest content is what's to come as we look at training this model, and then in the finale next week, we really put everything together. I mean, it's going to be a crescendo. It's going to get better and better. Hang in there. All of the good stuff is to come. So what we're doing next time, there's some more hyperparameters. I know that these hyperparameters can be a bit grueling, but this is where the really important stuff is learned. So there's some hyperparameters that control training that I'll explain to you. We're then going to set up something called a supervised fine-tuning SFT trainer, which is where it all happens. And then we're going to kick off training. You're going to be training your own proprietary large language model based on a LLaMA 3.1 base model. And we're going to be doing it in the next session. So I will see you there.